In this video, we'll look at estimation mostly, and then I'll say a couple things about hypothesis testing in probit and logit models. So probit and logit models are estimated by the method of maximum likelihood, which I briefly mentioned back in the topic we did earlier in the course on statistics preliminaries, but we didn't really go into detail on it. And we're still not going to go into great detail on it, but I want to do more than just sort of be hand-wavy about it. So this is not something I expect to, well, as we go through, I'll be more explicit about what I don't expect you to, know or be tested on. But I did want to sort of give you an overview of the process. So remember, y is Bernoulli. And so y is equal to 1 with this success probability, and y is equal to 0 with this sort of failure probability. Okay. And so what we do is we form the likelihood for observation I. So that's the probability of the observed value of y. And it's written typically as this script L. Y is the sort of random thing here. We're conditioning on the data x and parameters beta here. Okay. And it's written in this way, but just notice if you plug in success, y equals 1, then you have just this, and this all evaluates to 1. Okay, and if you have failure, y equals 0, this whole thing evaluates to 1. The exponent here would be 1, and so you're just picking out this bracket right here. So this is just like a convenient sort of compact way of writing a function that if you plug in y equals 1, you get this. If you plug in y equals 0, you get that. Okay. The sample points are all independent. So the likelihood for the whole sample, which is called the joint likelihood, is the product of all of the individual likelihoods. Okay, so you would take this sort of expression, and then you're taking the product of that over all the sample values I. Okay, the maximum likelihood estimate is the value of beta that maximizes this likelihood. Okay, so of all the possible values of the parameter vector beta, which unique value makes the observed data as likely as possible? Okay. It's usually more convenient to work with, in practice, the log likelihood. So just take the natural log of this joint likelihood we worked with, and notice that by properties of logs, what that's going to do is it's going to turn the product of these individual likelihoods into a sum of log likelihoods for each observation I. Okay. Because the natural log is a monotonic transformation, this doesn't affect what the maximum likelihood estimate of beta will be. So the value of beta that maximizes this will be the same as the value that maximizes this, which makes it an okay thing to do. The estimates are not obtained through closed form expressions. So unlike linear regression, where we have formulas for our beta hats, that's not true generally in nonlinear models. Instead, they're obtained through numerical optimization. And so that's sort of as far as we're going to take it in terms of the process. When you estimate these nonlinear models in Stata, you'll see before it reports the results, it'll report a number of iterations. And what it's doing is using these numerical optimization techniques to sort of search through the parameter space in an intelligent way to find the solution to the maximization problem. Wooldridge goes into some additional detail, and I'll refer you there for extra details. Okay. I don't expect you to be able to sort of write down the likelihoods or joint likelihoods or log likelihoods. Okay, I just want you to sort of be familiar in general with what this process looks like, especially in case you need to refer back to it, in future coursework or something like that that goes into more advanced methods. If you want to test a null hypothesis like this, which is, just that whether one of the betas has sort of any effect. So you can, the null here, beta sub j is equal to 0. That works exactly as with OLS. So Stata or any stats package will give you an estimate, beta hat, and a standard error. and you can just form a t-statistic. It has a t-distribution, under the null hypothesis, assuming a large enough sample size, and you can just apply the methods that you know. If you want to test restrictions on multiple parameters, you can do this, but you can't do it with the f-distribution and the f-test that we used for multiple regression. So Wooldridge talks a little bit about this. If you ever need it, you can sort of refer there, for more information. We won't do this particular thing with probit and logit models. Stata makes this pretty easy to implement. Basically, the main thing you need to do is just replace the regress command with probit or logit. And then remember that you need to look at marginal effects instead of the coefficient estimates themselves, in most cases, to interpret your results. Okay. So the linear probability model, remember, is just OLS, so this looks very familiar. Let npov here be the 0, 1 variable, the binary dependent variable. We are using female indicator, age and years, 4-category race ethnicity variable, years of education. We might want to use, in this case, sampling weights, and we should estimate robust standard errors. Okay, so you're familiar with all of that. If you want to estimate a probit model, just replace the regress with probit. Probit doesn't support analytic weights, A weights, so what you can do instead is use what are called probability weights or P weights. And then you want to estimate these average marginal effects here. All right, so let me try to explain what's going on there. This line, the margins command, is being used here with this option. And the dy dx says to compute average marginal effects. That's the dy dx. It's like the change in probability y is equal to 1. That's the dy, with respect to changes in x. And then the star or asterisk in there is telling Stata to do this for all explanatory variables. So that asterisk is like a wild card. You could potentially, like if you had a model with a very large number of explanatory variables and you were really interested in the marginal effects only of like a small number of them, or maybe just one, you could just tell it which variable you wanted marginal effects for. But this is a small enough model that we may as well just look at the marginal effects for all of them. And so that's what the star is doing. For logit, do the exact same thing with one change. Instead of using the probit command, use the logit command. All right, so that keeps it pretty simple. Notice here that I specified of course, the 4-category race ethnicity variable has to be specified with I dot because we need to tell Stata, I know this variable looks like 1, 2, 3, 4, but these are different levels, different categories, okay? The female variable is something more subtle here. So it doesn't actually matter for OLS whether you specify I.female or just female, but it does matter for probit and logit. All right, and the idea here is that for marginal effects, it's important, like you would use a different formula to compute these marginal effects depending on whether you're thinking of the variable as something that's maybe continuous, and so you can differentiate and think about an infinitesimal change in that variable, or it's something that's discrete where there can only be like step changes in the variable. Okay, and so there's no the female is not a continuous variable, basically, is the problem. So you can't use the version of the formula for continuous variables where we think about sort of instantaneous changes in the value of that variable. Instead, we need to be explicit and tell Stata that it is a discrete variable, and the marginal effects should be computed in that way. All right, so for marginal effects, it's important that all of the discrete variables are specified using that I dot syntax. All right, so that's sort of an overview of what's going on behind the scenes with the maximum likelihood estimation, and then what that code looks like in Stata.